Hello friends, welcome again to the tetrahedron chemistry classes. So guys, in today's class I am going to discuss S block elements, and in S block elements today we will discuss alkali earth metals. Okay, in my last lecture I have explained the alkali metals, where that is the group 1 elements. Okay, if you haven't seen that particular lecture, kindly go through the description box. I have given you the link of the group 1 metals, lectures of the group 1 metals. You can learn the group 1 metal also. Okay, and now I'm going to start this group 2 metals, which is technically known as the alkaline earth metals. Okay, so here you can see I have written the group 2, and here I have written the metals. Why they are metals? Because they are electropositive. They have the tendency to lose the electron to form the positive ions. Okay, and I have written here the less reactive, but please remember these alkaline earth metals are less reactive compared to the alkali metals. Okay, so if I want to complete this, so here you can write your lithium, sodium, potassium and so on. Please remember this particular point. These alkali earth metals are less reactive only compared to the alkali metals, and whatever the properties you have seen for your alkali metals in my last lecture, all those properties will also be given by the alkaline earth metals. Okay, they are very reactive, of course, but less reactive than the your alkali metals. That is the group 1 elements, right? This thing is very important to understand. Now you can see here, if I go their occurrence, so first of all you see here I have written beryllium, magnesium, calcium, strontium, barium and radium. These are the elements, and I have written their occurrence in the earth crust. So your calcium is actually the 5th most abundant element in the earth crust, and your magnesium is 6th, not 6th actually. It is error in this particular slide. Please remember, it is not 6, but your magnesium is 8th most abundant element in the earth crust. Okay, and strontium and barium, their occurrence is quite lower, while you can find beryllium rarely in the earth crust, right? And that's why it is not included in the true alkali earth metals. Later I will come to that particular important questions also. And your radium is the rarest, and which is the radioactive also. Please remember these things points. And if you want to know their trivial or the older name, then you can go through the textbook, right? Like your magnesium is known as the magnesia, right? And this beryllium is known as the beryllia, right? And then this is strontia, right? And this barium is the baryta, right? All these things you should know. Okay. And now if you want to know the electronic configuration, so I have already told you in my last lecture, you in chemistry basically, right? I am talking about the chemistry, not the mathematics. Okay, in chemistry, wherever we are talking about the magic numbers, these magic numbers are 2, 8, 8, 18, 18, 32. What is the use of these magic numbers? I have also explained in my last lecture of the alkali metals, but if you are new here and watching video for the first time, I am explaining the things again, right? You have to remember these, or you have to learn these magic numbers. And in the periodic table, if you know the atomic number of any first element, then you can get the atomic number of remaining elements present in the particular group. For example, beryllium is 4, and you know this 4 is greater than 2. So you will start from here. If you add 8 to this 4, it will give you the 12. So 12 will be the atomic number of the magnesium. And again, if you add another 8 to the 12, then it will give you the 20, which is the atomic number of the calcium. If you add 18 to the 20, right, that means you will get the atomic number of the strontium, that is 38. If you add another 18 to the 38, then you will get the 56, which is the atomic number of the barium. And then if you add 32 to the 56, then you will get the 88, which is the atomic number of the radium. Okay, and if you want to write the electronic configuration of them, then you can see for 4 you can write 1s2, 2s2. This is the electronic configuration of the beryllium, and you know this 1s2 is the electronic configuration of the noble gas, and that noble gas is the helium. So instead of writing 1s2, what I can do, I can write that helium in the square bracket, which shows the electronic configuration of the helium, and remaining part is the 2s2, which I have written here. Similarly, if you go for the electronic configuration of the magnesium, then you can write 1s2, 2s2, 2p6 and 3s2. And if you know, see, if you check this this part actually up to from 1s to 2p, so 2 plus 4, 4 plus 6, that is 10, right? That means total 10 electrons are here. So this is actually the electronic configuration of the neon. So what I can do, I can write neon here, and then I can write the 3s2, which is the which are the 2 electrons present in the 3s orbital. So in the same way, if you continue to write the electronic configurations of these, then after neon you are having the argon. So you can put this argon in the square bracket, and after that you will write the 4s2 here, and after argon you are having your krypton. Okay, so this is the electronic configuration of the krypton, and this is 5s2, and then you come to this one, xenon, electronic configuration of the xenon, and then 6s2, right? And then you are having the radon, and then you can write 7s2. So your you can see here your last electrons actually are entering in the s orbital. This is the region. This group 2 is also included in the group 2 elements. Okay, so this is the use of the your you can say the magic numbers. Okay, and now moving to the next thing. The next thing is, see, before moving to the next thing, I want to give you an important information about these compounds also. You know this magnesium is very important, which is found in the various biological systems, and its hydroxides is used in the antacids, right? So okay, and why? Because from the intestines this magnesium hydroxides absorbs water, and which loosens the stools actually, right? So it is occasionally used for the removal of the constipation, magnesium hydroxide. But please remember, compounds of beryllium and compounds of barium, they are very toxic, and you have to be very carefully while dealing with the compounds of these two, barium and the beryllium. They are very toxic. Like, see, beryllium, if you go for the toxicity of the beryllium, see, beryllium is basically a skin irritant, okay, and it can result dermatitis, and sometimes it is all, see, if inhale in certain quantities, right, then it can provide a person acute pneumonitis, right, and chronic pulmonary diseases can also be caused by the beryllium poisoning. Similarly, your barium compounds, right, these barium compounds are also very toxic, which actually results in the watery diarrhea, right, vomiting. It can induce the sensation of the vomiting, right, abdominal pain it can give. So please, while this is something very important, while magnesium hydroxide is actually used in the medicines as antacids, while the compounds of the beryllium and the bariums are quite toxic, you should know these things. Okay, now moving to the next slide. Okay, now these are the important questions, especially for the beginners. Why the group 2 metals are called the alkaline earth metals? So I have summarized the 2 points here. You can see here. See, if you dissolve the metal oxides, right, they are hydroxides, and how we can form the hydroxides of this? It's quite simple. If you have, say, magnesium oxide, right, and if you dissolve this magnesium oxide into the water, it will give you the magnesium hydroxide, and this reaction is true for the remaining of the members also. Okay, magnesium hydroxides. So basically their hydroxides are alkaline in nature. That's why the alkaline word is there. Examples are the magnesium hydroxide, calcium hydroxide, strontium, and the barium hydroxide, etc. And their oxides, right, I have written in case of magnesium oxide is the example. Like their oxides like MgO, CaO, they are earthen in nature. That means they found in the earth crust, and earlier chemist, actually older chemist, or you can say the alchemist, what they understand, why they actually given the name this earth actually, because they are very high melting. These oxides are very high melting. So whatever the temperature available for the in the past for the older chemist, right, at that particular temperature these compounds are actually not melting, right, and which the things which are not melting, the scientists call them as the earthen. That's why this word earth is there. And since they can remove electrons to form the electropositive ions, that's why metal is also there, and it completes the name alkaline earth metals. This is something very important which you should remember, guys. Very important question, right? Now what is the next question? What it says, why beryllium is not a true alkaline earth metals? Now it is quite easy. I have given you the 2 points in the above question, like this is the point 1, this is the point 2. So you know the oxides and hydroxides of beryllium, if you make the hydroxides of the beryllium and oxides of the beryllium, they are actually not at all alkaline. They are amphoteric in nature. Okay, they are amphoteric in nature, and since they are amphoteric in nature, they are not actually alkaline. So they are not alkaline, so we cannot include the compounds of the beryllium in the alkaline earth metal. So in a true sense, right, however it is very rare to find this particular explanation in the textbook. In many of the textbook, in certain standard textbook you can find. So for this particular region, that is the it cannot fulfill the point number 1. So their hydroxides are or oxides are not alkaline, but they are amphoteric, so that's why they are not alkaline earth metals. However, they fulfill the second criteria. They are earthen, actually high melting. Okay, so this is something, another very important point which you should remember. Now moving to the next slide, what it says, okay, their occurrence, how you can find these elements in the nature. See, magnesite is the ore, okay, which is the ore of the magnesium carbonate, okay, and magnesium is abundant in the nature, if you know, okay. And dolomite is another very important ore from which you can extract your magnesium. However, calcium is there, but from this you can extract magnesium only, okay. Then in the abundant amount rather, okay. And then you are having the carnallite. Carnallite is a kind of the double salt, like earlier you can see the dolomite is the double salt. Your carnallite is also the double salt, which is nothing but the potassium chloride and the magnesium chloride double salts, and it is hexahydrated. Please remember, water of hydration is 6 here. So from here again you can collect your, or you can extract your magnesium. Then Epsom salts are very common. Epsomite is the name. Magnesium sulfate, heptahydrate. And then you are having the limestone, which is the source of the calcium. Marble, chalk, calcite, everything, right? Lots of things are there to extract the calcium. And then anhydrite is again there, which is nothing but the calcium sulfate. And gypsum is very important compound in the cement industry, which is the source of the calcium. And there's fluorspar. You might have heard about the fluorspar, which is commonly used for the extraction of the calcium, okay. And then you are hydroxyapatite and the phosphorite. So these are the abundant ones, that's why their ores are given here, while others are rare actually. Okay, so my next slide is the atomic size or the ionic size. So however, I have written only the atomic size here, but whatever I will explain for the atomic size, that will true also for the your ionic radii. Okay, so you can see here the group 2 elements. See, these are the group 1 elements, lithium, sodium, potassium, and it goes up to the rubidium. And these are the group 2 metals, that is the alkaline earth metals. Starts from the beryllium, and the group goes like that: magnesium, calcium, strontium, barium, and the radium. And if you compare the size, you know the down the group size increases. So definitely the down the group size increases for the alkali metals as well as for the alkaline earth metals. That's why you can see here this circle is smaller, this circle is quite bigger, this is another relatively bigger, and this is the biggest one. This shows the increase in the size, okay. And now if you compare, see, they are the bigger in the size. If you move across the period, you know, in the across the period size decreases, which I have written here, okay, and down the group size increases. That means they should have the smaller size when compared to the your alkali metals, of course, actually, right? Because when you move across the period, effective nuclear charge becomes more important, which pulls the electron cloud strongly towards the nucleus, which decreases the electron cloud, and hence the size also decreases. Okay, so however, their size is bigger than the p block elements, but their size, whether the atomic size or the ionic size, it is smaller than the alkali metals. You should remember this particular point. Okay, and then there comes the beryllium. Beryllium differs much more than the rest of the group members than lithium does from the members of the group 1. As you know, the lithium has the significantly different properties and the anomalous behavior, and this behavior is quite different from the remaining members of the groups. Same is true for the beryllium also. This beryllium is having the anomalous behavior due to its very smallest size actually. Okay, this size is very small for the beryllium, so it actually differs in the properties significantly from the rest of the members of the groups. Okay, and this difference in the properties is much more pronounced when you move from beryllium to magnesium than it is for your lithium to sodium. This is something very important. The main reason basically is that the beryllium atom or the beryllium ion Be2 positive, they are very small actually. Okay, so when they are very relatively small when compared to the magnesium, in fact it is beryllium 2 positive, and if you go for the data wise, right, so I can write here, say for example, this is your Be2 positive, okay, and this is your Mg2 positive, right. So basically this magnesium is 4 times greater in size than the beryllium. Okay, that means it is extremely small. Okay, while this difference is see here 4 times, this magnesium is 4 times greater in size than the beryllium, but this much of difference in size is not there in case of the lithium and the sodium. That's why your beryllium significantly differs from the rest of the members of the groups. Okay, and like you can see, the your lithium shows the diagonal relationship with the magnesium. Okay, and then your beryllium, actually if you move, the beryllium shows the diagonal relationship with the aluminium. We'll discuss the diagonal relationship if the time permits. Okay, these things are very important. Okay, now then comes to the see, and whatever the things I have explained, they are equally true for the atomic radii also. Okay, and then we can move further and go through the physical state, right, how actually they look like. Physical state is rather important. Okay, so basically they are also soft but harder than the alkali metals. As you can remember or you can recall, in case of the alkali metals, I have shown you the video also, they can be cutted with the help of the sharp knife of the blade. Similarly, these metals are also soft, but they are comparatively harder when compared to the your first group member. So what is the reason behind this? See, reason is the metallic bonding. Okay, and if I go back again and again, I need this particular slide. You can see here 2 electrons are present in the outermost shell of every element present in the group 2 metals, that is in the alkaline earth metals. So these 2 electrons are involved in the metallic bonding, while in case of the alkali metals only 1 electron is there in case of the s orbital. So in case of the alkali metals, your metallic bonding is weak because only 1 electron was there, while in case of the alkaline earth metals 2 electrons are there in the s orbital, so their metallic bonding is comparatively harder than the alkali metals. That's comparatively stronger than the alkali metals. That's why they are hard when compared to the alkali metals, but still they are soft with the remaining metals. Okay, and this hardness decreases down the group, right, because the size increases. Okay, and when the hardness, see that since they are harder than the group 1 elements, so they are less ductile and less malleable than the group 1 elements. Ductility, you know, ductility is the ability of the particular metal to draw the wire of that particular metal. Malleable, that means you can hammer that particular metal to convert it into the sheets. That is the malleable character. So the ductility as well as the malleability is little bit of the lower side, as they are little bit harder when compared to the group 1 metals, and this hardness decreases as we go down the group. So this is something very important. Okay, and after that, see what is there in the next slide. Okay, see ionic radii again. See, I have explained you. See here the difference is what you see. This lithium, it is the lithium atom, it is somewhere around 152 picometer, while lithium ion is 176 picometer. It is quite smaller, and you know the fact your cations are always smaller than their parent atoms, because in the formation of the cation you have removed the electrons. So the effective nuclear charge increases, which pulls the remaining electrons more strongly, which decreases the size actually. Okay, now if you go for the beryllium, so for beryllium it is 112 picometer, and when you form the beryllium ion, it is 31 picometer. So if you take the difference actually between the two, okay, so I can write here 152 and then the 76. So 6 is here and 76 is there. Okay, and if you write 112 here, so you can write 31 here, so 1, and then you can see here 81. So this difference is quite large actually. That's why beryllium ion actually is important. Okay, and you know the ionic radii also increases when you go down the group. Okay, so beryllium is smallest in size in the group. That's why it is having the anomalous behavior. Now moving to the next slide, and this is the comparison you can see here. See atomic radii of the lithium to see if you check this atomic radii between lithium to sodium ion. See, this is again a very important data which you should know. 0.186 nanometer. Okay, and for lithium is 0.152 nanometer. So difference is what? 4 and 3. Okay, that means 0.034 nanometer is the difference. You can easily convert this nanometer into the picometer. However, I am not going to convert this. However, it would be rather important, rather good, or rather well if I put this value also in the nanometer, in the picometer, as I have quoted earlier. Okay, now if you check this here, beryllium and magnesium difference. So this is 0.160 for beryllium nanometer hai. Okay, and then this is 0.112. So this will give you 8 and this will give you 40. So 0.048. So this actually difference between the size of the beryllium ion and the magnesium ion, which actually gives the distinct behavior of the beryllium to the magnesium when compared to the lithium to the sodium. Okay, this already I have explained to you. And then what I have written here, let me check why group 2 elements are less reactive than the group 1 elements. Okay, this is due to the smaller in size. Okay, so as we move across the period, the reactivity actually decreases, which you should know, and their size actually, if you can see the group 2 elements actually, right? So group 2 element, they are having, see, lithium is 3, beryllium is 4. So here beryllium is smaller, and your sodium is 0.186 nanometer and your magnesium is 0.160 meter. So their size is smaller. Okay, and so when their size is smaller, so this difference in the atomic radii, you can see their atomic radii is smaller. That means their effective nuclear charge is very high. These elements are rather reluctant to remove their electron to participate in the reaction. That's why their reactivity is lower than the group 1 elements. This is again depends on the size and the effective nuclear charge, which is the very basic concept. Okay, so my next slide is the ionization potential or the ionization energy. For example, if I write the electronic configuration of the sodium, right? So this is Na and this is 11, and if you write the electronic configuration, it is nothing but 1s2, 2s2, 2p6 and 3s1. Okay, so if I supply some energy actually to it, right? So I can write ionization energy. Okay, ionization energy. So it will form Na positive. that means removal of the one electron. So it will attain the configuration of the neon, which is 10, which that means the 10 electrons are here. And then if you compare this with the magnesium, right, I can write the magnesium here. So magnesium is your 1s2, this is 2s2, and this is 2p6, and then here 3s2, okay, 612. Okay, now see, if I supply one electron to this, okay, and then it will form the Mg positive, okay, and you are having totally 11 electrons. So why I have written these two configuration? It is something very, very important. So if you see here, first ionization potential of the alkali metals, are quite lower. Why quite lower? See, because they are having only one electron. If I remove one electron from here, actually it will easily attain the configuration of the nearest noble gas, which is the most stable condition for it. That's why very little amount of energy required to remove the electron from here. Okay, while for the group 2 metal, and you know, when you move across the period, so group 2 metals will have the lower size. So please remember, group 2 metals actually will having the lower size, or smaller size rather, lower or the smaller size. Since the size of the alkaline earth metals is small, okay, that means their effective nuclear charge is quite high, and due to this high effective nuclear charge, this magnesium is quite reluctant to remove the electron from here. So it will require higher amount of the energy to form the Mg positive ion. It is quite important. That's why if you compare the first ionization potential, then first ionization potential of the alkaline earth metal would be higher when compared to the alkali metals. Now, if you supply, say, little more energy to it, plus I can write IE, or IE second rather, it was IE first actually. So you might have formed Na2 positive, and you know, because since it has this sodium ion has attained the electronic configuration of the nearest noble gas, so this second ionization potential is quite high. Okay, but in case of the magnesium, if you supply some more energy, IE I can write, so it should be the capital E, sorry, this is 1 electron 5, okay, and IE is there, right? And if you supply more energy, which is the second ionization potential, okay, so it will again lose the electron to form the Mg2 positive, and it will have the now 10 electrons. So second ionization potential would be quite lower when compared to the alkali earth metal. So this is the thing which you should remember, which I have summarized here also. First ionization energy of the group 1 elements are lower than the first ionization energy of the group 2 elements, okay, right, due to the size. Second ionization potential of group 1 elements are quite higher when compared to the group 2 elements. The reason is that which I have explained here. So this is something very, very important which you all should know, especially beginners. Okay, so this lecture is not only for the advanced learners, of the advanced chemistry, but it is these lectures are also for the beginners, like the students who are studying in the class 11th or the class 12th or in the BSc. These lectures are equally important for them, because it is my general tendency, whatever the topic actually I upload in my channel, I actually complete the lecture thoroughly, right from the basics which is required for the beginners and up to the most advanced point, right, like your for CSIR net or GATE or the other examinations. I hope this is clear to you. Now next is what? Beryllium compounds are typically covalent, while magnesium, calcium compounds are ionic. Again, see guys, this is something very, very important. So since I have explained this one, so I don't need this place, so I am removing it. Okay, fine. So why this actually happens? I already told you this beryllium, Be2 positive, and you have already seen this is very, very small. Okay, so its polarizing power is very, very high. Its polarizing power is very high, and whenever the polarizing power is very, very high, it can easily polarize the anion, and your compound will have the significant percentage of your covalent character. That's why due to this extremely small size, your beryllium compounds are covalent, right? While magnesium, you can see the size is quite good, For calcium and so on, the size is quite good, and that's why they are ionic in nature, and this ionic nature of the compounds increases when you go down the group. So here you can see, as you have seen earlier, your alkali metals are very good reducing agents. Okay, and these alkaline earth metals, that mean the group 2 metals, they are also a very good reducing agent, but their reducing character is lower than your alkali metals, because alkali metals are more electropositive due to the bigger size, and the size of the alkaline earth metals is quite smaller when compared to the alkali metals. That's why due to the effective nuclear charge, they are little reluctant to release their electrons, so that's why they are not that reducing in nature. And for the beginners, it is very important. If you go for the modern definition of the oxidation and reduction, that means decrease in the oxidation number, that means decrease in the positive charge. And how we can decrease the positive charge on the particular metal? By supplying the electron. So these two groups in the periodic table, 1 and 2, they all can actually give the electron to the particular species, so they can act as the reducing agents. But please remember, alkaline earth metals are less reducing than the alkali metals. Please remember. Okay, so here you can see this is the reducing order, which is increases in that manner, because you see it is smaller in size. Okay, so when it is smaller in size, its reducing character is lower, and as we go down the group, the size increases. That means the removal of the electron becomes very easy. That means the metallic character increases, so the reducing nature also increases. Okay, but group 2 metals are weak reducing agents compared to the alkali metals. Okay, and the reducing character of any metal is best measured in terms of the electrode potential. Okay, so here see what actually you can understand from here. However, this thing I think I have also explained in my very short list of electrochemistry. I couldn't complete that electrochemistry lecture series, but I have explained this thing there also. Well, you should remember this particular point, right? And say, I am writing here, higher the value of reduction potential, higher would be the tendency of metal to get reduced. And when it is getting reduced, that means it is acting as a oxidizing agent. Please remember this point. In any redox reaction, the species which is undergoing reduction will act as an oxidizing agent, and the species which undergoes the oxidation will act as a reducing agent, right? And for alkali metals and alkaline earth metals, please remember, for both of them, the value of the reduction potential is quite low. Reduction potential value is quite low. Since the reduction potential of these two are quite low, that means they will not have a general tendency to undergo reduction, rather they will undergo the oxidation, and the species which is undergoing the oxidation will act as a reducing agents. Okay, but the value of the reduction potential of group 2 elements, you can see, is higher when compared to the group 1 elements. Since the value of the reduction potential is higher for them, they will have the higher tendency to undergo the reduction, and that's why they will act as a oxidizing agent. This is just for the explanation. However, they are not oxidizing agents, but this is just the explanation when you are comparing to the reducing nature with that of the group 1 metal. Okay, this is something again an important feature which you should remember. So whether it is calcium, whether it is magnesium, right, they all are very good reducing agent. Now moving to the next thing, metallic character. Okay, metallic character means simply the removal of the electron. Okay, so alkali metals and alkaline earth metals, as you know, when you move across the period, the size decreases, and when the size decreases, see, I can write here, when you move across the period, size decreases, and when you go down the group, the size increases. Okay, now you are moving from lithium to beryllium. That means size actually decreases. When size decreases, that means effective nuclear charge increases, and when effective nuclear charge increases, then the removal of the electron becomes little difficult, and when the removal of the electron become little difficult, that means it will form positive ion but with difficulty. That means lower metallic character. That's why alkaline earth metal are less metallic. However, they are they are again like alkali metal. They are silvery white, or sometimes not silvery, but the white actually. Okay, so most metallic due to the alkali metals are more electropositive in nature. Please remember this particular point. Okay, and same is true for the electropositive characters. Metals have a tendency to lose electrons. This I have already explained to you, and this is the periodic variation, and you can correlate this with the ionization potential. Higher the ionization potential, lower the metallic character, which I have already explained to you. Okay, I don't think whether I should go again and again for the same kind of the explanation. Now moving to the next slide, what it says, melting and boiling point. Rather, see again, you can see here melting and boiling point. These alkaline earth metals are they are having the 2 electrons. Please remember, they are having the 2 electrons. When they are having the 2 electrons, that means their metallic bonding is strong. When their metallic bonding is strong, so they should have the higher melting point. Of course, a higher boiling point also when compared to the group 1 metal. It is something very, very important. So here you can see for alkali metals, if you go down the group, melting point decreases, and this is true for the alkaline earth metal also. Okay, so group 2 elements have the higher melting and boiling point than the group 1 elements. The reason is what? Because 2 electrons are present here, so metallic bonding is a little bit stronger here, and when metallic bonding is little bit stronger, it simply indicates that it should have higher melting at the boiling point. However, pattern is very, very irregular. These metals cannot actually follow the regular pattern, okay, of your melting at the boiling point, right? So why this irregular pattern is there? As I have see in case of the lithium, in case of the alkali metals, this is quite fine actually. See, lithium is the you can see this is having the melting point, and then your sodium, then potassium, rubidium, and cesium. Okay, so this is according to the size. This is quite fine. But in case of here, you can see melting point of beryllium. After beryllium, there comes the calcium. There is no place for the magnesium. Okay, and then strontium, barium, and the magnesium goes last. And similarly, if you see for the boiling point, then beryllium. After beryllium, then you are having the barium, and then calcium, and then this one. So pattern is not regular in that case. Okay, see these metals actually, right? They have the different crystal structures. When they have the different crystal structures, that means crystal structure, when the crystal structures are different, definitely their lattice energy would be also different, right? And due to this, irregular pattern is observed. Fine. So now moving to the next slide, density. Your another important aspect is the density. So for density, you can see here alkaline earth metals, they have the low densities. For density, you know, simply density equals to mass over volume. There is no problem in that. Density equals to mass over volume. That means when this increases, this decreases. So when you move across the period, your size decreases. And when the size decreases, definitely density increases. Okay, that means your alkaline earth metal should have higher density than the alkali metals, and it is true also. Alkaline earth metals are denser than the alkali metals due to this particular concept. Okay, down the group, the atomic masses increases. You know, when you move down the group, whether it is whether you are observing for the alkali metals or the alkaline earth metals, it will not make any difference. Okay, so down the group, atomic mass increases, which more than compensates the bigger atomic size. Therefore, that's why the density is less than the density of the magnesium. Why actually this is happening? Okay, fine. There is nothing. Next thing is quite simple. This I have already explained you in my first lecture also. See, when you move down the group, both things increases. Your atomic mass increases, as well as your atomic size also increases. But which one is the dominating factor, right? That dominating factor will decide the density basically. So what I have written here, down the group, atomic mass increases, which more than the compensates the bigger atomic size. That means it will compensate the atomic size. That means the atomic size also increases, but that increase is not that much when compared to the atomic number. So atomic number increases, that means mass increases, so density also increases. Right? That's why down the group density increases. This I have explained to you. Calcium is less denser than the magnesium because of the presence of the penultimate d orbital. This is rather simple. I have this is written here actually. See, density of the calcium is lower than the density of the magnesium. It is written here. Okay, there is no problem in that. So what it says, you know, the atomic number for this magnesium is 20. It is for 12. If you write the electronic configuration, somewhere after that it will have the 3d orbitals vacant. Okay, vacant 3d orbitals. That means volume increases. Volume increases. When volume increases, definitely density decreases. That's why magnesium is having the lower density, calcium is having the lower density than the magnesium. This was quite simple. Now moving to the next thing, which is the flame coloration. Flame coloration I have also explained in case of your alkali metals, but here you can see, if you see here, I have from where I have started. I have started from the calcium, and then strontium, and then barium, and the radium. So I didn't include the magnesium here, and I didn't include the beryllium here. That means beryllium and magnesium, they will not give the characteristic flame to the color. Why? Because their ionization potential is quite high, and very high energy is required to remove the electron from them. So that's why your beryllium and magnesium will not impart any color to the Bunsen burner or the Bunsen flame actually, right? While your calcium is brick red, okay, and strontium is your crimson red, and your barium is apple green, and radium is the crimson. So these colors are there. So these properties generally shows only in the S block elements. D block elements do not impart any color to the Bunsen flame. This is again an important thing here. Okay, and their color are rather pale actually, because their potential, their ionization potential is quite high. So high energy is required. So they are not give the very bright color like you have observed in case of the alkali metals, but in that case the colors are little pale when compared to the alkali metals. Okay, now moving to the next important property. Okay, so now let's move on to the chemical properties of your group 2 metals. Let's see what is the first chemical property of this. First is the reaction with the oxygen, right? So basically what I have written here, oxygen with air. You know, the air also contains the nitrogen, and nitrogen is quite unreactive. So we later on we will also see the reaction with the nitrogen. First of all, you can see here all the metals of group 2 elements will actually group 2, right? All the metals of the group 2, they will combine with the oxygen to form the metal oxide. Okay, and you can see here just beryllium combined with this one, and it forms the beryllium oxide. Similarly, magnesium combines with this one, it forms magnesium oxide, right? All these reactions are here, and you can see here beryllium, magnesium and calcium. If you go through the first three actually, beryllium, magnesium and calcium, they when heated with the oxygen, they form the monoxides. Please remember this point. Beryllium, magnesium and calcium, they only form the monoxides because their size are comparable with the oxide ion only. So they can accommodate only the oxide ion, or they can only cater the oxide ion. So they will form only the monoxide. Okay, right, like I have written over there. While your strontium and barium and radon, however, we can exclude the radon because it is radioactive, so we rather use this compound. Okay, but it is true that the strontium, barium and the radium, they also form the peroxide. Why? Because their size is little bit bigger than when compared to the earlier three members, so they can cater the bigger oxide ions also. So that's why they also form the peroxide. It should be it should be noted, and it is very important. And the reaction is MO2 type. You know, this is the formation of the peroxide, and these are the formation of the monoxide. Okay, so this is, you can see the M2O2 whatever I have written here. Okay, so this reaction is very important. So the important thing is that when you expose these metals with the air actually, so they readily form these oxides, and due to the formation of these oxides actually, they achieve the crystalline nature, or crystalline, they become the crystalline solid, and these oxides are basic in nature, but not your beryllium oxide. As at the start of the lecture I already told you that the beryllium oxide nature is not alkaline, that's why it is excluded from the list actually. It is not a true alkaline earth metals, right? This I have already explained to you. And see, the basic strength of these oxides basically increases when we go down the group. This I have already explained to you. Now you can see one more important aspect here. If you have beryllium oxide, right, say, so the important thing about these oxide you should know, this is your beryllium oxide, right? This beryllium oxide is very hard in nature, okay, and this is having the coordination number of 4:4. That means one beryllium is surrounded with the 4 oxygen, and one oxygen is in turn surrounded with the 4 beryllium. So 4:4 is the coordination number for this one. While for rest of the oxides, if you take the magnesium oxide, like if you take the calcium oxide, their coordination number is 6:6, obviously due to the bigger size, okay, due to the bigger size of these metals. So 6:6 coordination number is there in that case. And these oxides, whether it is your beryllium oxide or magnesium or calcium oxides, they are quite stable, okay. So why? Because they are having very high lattice energy. Due to their very high lattice energy, these oxides are very stable, right? And if you take one more important data, like you are having your, say, beryllium oxide, okay, sorry, beryllium oxide and your magnesium oxide, right? These two are water insoluble. They are insoluble in water, okay. And while rest of other oxides are soluble in the water, and the basic strength increases down the group, as I already told you for them. And see, what actually happens in case of this magnesium and the calcium oxides. If you remember, or if you have learned, or if you have studied your metallurgy part, then you know the calcium oxide and the magnesium oxide, these two, right? If I write here calcium oxide and magnesium oxide, these two are used in the linings of the furnaces when you do the metallurgy. Why? Because their melting point is quite high. So basic lining, so basic nature lining which are there in the furnaces, actually in that case your calcium oxide and the magnesium oxides are used because they are having the very high melting point, okay. And then you can see here, we can move further. Here you can see the very important reaction which actually I have missed actually to explain. So this magnesium, when it is reacting with the air, and I already told you just a few moments back, this air contains the oxygen as well as the nitrogen. So when the magnesium combined with the oxygen, it forms the magnesium oxide, as well as when it combines with the nitrogen, it forms the magnesium nitride of the type Mg3N2. This actually reaction is a exothermic reaction, and it produces a very important, very shiny, beautiful dazzling flame, okay. And this dazzling flame is used in the flash photography. You can see the picture here. This is the dazzling flame which is produced by this particular reaction, because it is exothermic, actually catches fire. It gives you the flash like that, okay. So this method is used in the flash photography. This is something very important. So I have written here, you can see, okay, this I have completed. Then next is the reactivity, okay. Massive form or the big crystals of the beryllium only reacts with the above 600 degrees centigrade. That means towards oxygen your beryllium is unreactive. So that means if you want to produce beryllium and you want to burn that beryllium in the oxygen, so that would be a very hard reaction, because beryllium only reacts with the oxygen after or the above 600 degrees centigrade. See, if you have the big crystals of the massive or the massive forms of the beryllium, but if you finally divided this crystal into the fine powder, when we have the grains are having the much larger surface area. So due to this larger surface area, reaction rate goes higher. Okay, so when you convert this massive form into the powder, only then you can burn your beryllium in presence of the oxygen to get the beryllium oxide. Otherwise it is not possible. And next, as you can see here, thermite reaction basically. Okay, so what are the thermite reactions? Thermite reactions are the reactions in which the metal oxide is reduced to metal by using the aluminium as reducing agents. So you can see metal oxide is reduced to the metal by using aluminium as reducing agent. This is the thermite reaction, very famous thermite reaction. Okay, so this magnesium oxide is also used in the thermite reaction also. This is something very important. Why? Because when magnesium burns, it forms the magnesium oxide, and that this magnesium oxide can be reduced to the magnesium by using the aluminium. This is used in the thermite reaction. This is another very important aspect which you all should know. Now moving to the next property. Okay, reaction with the nitrogen. So one very important thing about the reaction with nitrogen I have already explained here. Okay, now moving to the next one. Here you can see what it is saying. Okay, if you have followed my last lecture, which I have uploaded day before yesterday, okay, there I have explained that lithium forms, see, among your first group elements, like your alkali elements, only lithium forms the Li3N, that means lithium nitride directly. Okay, but in case of the group 2, metals, all metals will form the nitrides. Why? Because their size is smaller than the group 1 metals, and the nitride actually is the N3 negative is the quite small one, so it can readily formed, this nitride are readily formed by the group 2 metals when compared to the group 1 metals. In the group 1 only lithium can form such nitrides. As we go down the group, the size of the metal or the ion increases, therefore the nitride formation tendency decreases. Please remember, when the size of the metal, ion or the metal increases, then the nitride formation tendency decreases. So for the alkali earth metals, while there is no question of this decreasing reactivity or decreasing order in case of the alkali metals, because only lithium can form the nitrides. Okay, this is something very, very important. And why actually this happens? This is another, there is another very important aspect here. You can see lattice energy is high for these magnesium nitrides. So whatever the nitrides you will form, for them lattice energy quite high. Why lattice energy is quite high? The high charge is present on the metal, like they all metals, these all metals are 2 positive, and your nitrogen is 3 negative, this high charge. Due to the presence of this high charge, this crystal is very, very strong, the lattice energy is quite high. Okay, and the nitrogen is very, very stable, and we need very high energy to form the N3 negative. So from where we can get this high amount of the energy? Actually this high amount of the energy comes from the lattice energy when your nitrides are formed. So whenever the nitrides are formed, the energy is released, and that energy is utilized by the nitrogen to convert nitrogen into the N3 negative. Okay, so this concept, this basic concept you should also know. Okay, this is something, another very, very important aspect. And here I have written the ease of formation of nitride decreases from beryllium to barium. Okay, fine. Earlier in the slide I have already told you, these are not my slides, these are the downloaded slides, but there was an error in that case, right? So it is not increases, it is decreases, as I have given you the explanation for this. I hope this is fine. Now moving to the next one. So when these nitrides are dissolved into the water, they forms the hydroxides, especially this is the magnesium hydroxide, and they liberate the ammonia. So whether you do the reaction with this one or with the calcium nitride, it will always eliminate or evolve, not eliminate, evolve ammonia, and metals get dissolved into the water to form the hydroxides, basic hydroxides. Okay, now moving to the next one, reaction with the water, reaction with water or the moisture, another very important aspect. Metal, you take the 2 equivalents of the metal, they react with the 2 equivalents of the water, and they form the magnesium hydroxide of MOH whole twice type. with the evolution of the hydrogen. That means from the water they can remove the hydrogen. So if you write the reaction with any of the like say you are having say magnesium, okay, and you are dissolving your magnesium into the water, so it will form magnesium hydroxide and it will liberate hydrogen gas. So 2 and 2, 4. 4 hydrogen atoms are required, so you should take 2 of this one, and when you take, then the oxygen becomes 2, okay, and Mg, okay, fine. This reaction is quite fine. So this hydrogen evolution occurs actually. And the reactivity with the water of these metals increases when we move down the group. Okay, this is the same region or the same explanation. See, as you know, the reactivity increases down the group, so it is true in that case also. Fine. And you can see the beryllium does not react with the boiling water. This is something very important. Beryllium, as I already told you, beryllium is very special due to its very smallest size. So beryllium actually does not react with the steam. It will not react whether you take the cold water, you take the boiling water, or you take the fuming steams, right? So beryllium is unreactive at all. While magnesium will react only with the boiling water. That means if you pass the steam over on the magnesium, only then you will get the magnesium hydroxide. Okay, so this should be steam, right? So I should have write here steam. While calcium, strontium and barium, they react vigorously with the cold water. If you take the cold water, they react with vigorously with them. Okay, so this you have to remember. Now you can see the solubility. You can see for the solubility, please remember down the group the solubility of these metals increases. Okay, when you dissolve into the moisture down the group in the water, the solubility increases for these metals. And when the solubility increases, in the same manner your basic nature also increases, right? And why this happens, you can see here. As we go down the group, we know the size of the metal increases, and when the size of the metal increases, lattice energy decreases, rapidly decreases. This I have already explained to you in my last lecture also. But if you are if you haven't seen that particular lecture and you are following this lecture for the first time, then you should remember down the group lattice energy decreases, okay, and your hydration energy also decreases. So all things, see, when the size increases, hydration energy decreases, lattice energy decreases. Now which one would be the deciding factor, right? Will decide the solubility. Okay, so in that case you can see the hydration enthalpy decreases, but it decreases rather slowly. But this decrease in the lattice energy is quite sharp, right, and quite high. So it is a dominant factor, right? It is a dominant factor, and when it is a dominant factor, it will increase the solubility. Okay, and when your hydration energy is the domination factor, then it will decrease the solubility. So in that case, you can see here when we move down the group, as we can see, the solubility increases, right? So why the solubility increases? Because your lattice energy much more rapidly than that of the hydration energy. And your beryllium hydroxide, I already told you, it is amphoteric in nature. That's why beryllium is not included in the true alkaline earth metals. Okay, and then there comes the magnesium hydroxide, which is your antacid. So that is MOM, milk of magnesia, right? So why the milk of magnesia? Magnesia is the trivial or the older name of the magnesium, and the hydroxide of this appears like actually milk. It is white in color, so that's why the name is given milk of magnesia, and it is antacid. So if a person is suffering from the slight constipation, right, not the chronic constipation but the sudden constipation, then for this your magnesium hydroxide is used. So what this magnesium hydroxide does, this magnesium hydroxide actually absorbs the moisture from the intestine and loosen the stool, and the bowel movement will occur now properly, and the person will have the relief after taking this magnesium hydroxide. The person will have relief from the constipation. This is another very important application. But remember, you can never use barium hydroxide, as your barium and beryllium are toxic in nature. So we can never use the barium hydroxide for this one. So this I have written here, barium hydroxide, which is toxic, most soluble and as strong as alkali as NaOH. So it is just like as strong as NaOH as alkali. Your metal reacts with the hydrogen. If you heat these two together, it will form the metal hydride. Okay, like magnesium form the magnesium hydride and calcium form the calcium hydride. And the technical name of calcium hydride is the hydrolith. Please remember, you may have the objective type of the question in your competitive examination. What is hydrolith? Hydrolith is the calcium hydride, which you should remember. Okay, this is another very important thing. And beryllium hydride BeH2 can however be prepared by reducing beryllium chloride with the lithium aluminum hydride. It's a very strong reducing agent. Why this happens actually? Because this beryllium, due to the smaller size, it is quite unreactive towards hydrogen also. So if you try to heat this beryllium with the hydrogen to get the beryllium hydride, then the reaction is not possible. So for the synthesis or for the preparation of beryllium hydride, you have to react with the beryllium chloride. First you convert beryllium into the beryllium chloride, and that beryllium chloride with the beryllium chloride is reduced with the help of the lithium aluminum hydride to get the beryllium hydride. Okay, so this is the reaction which I have written here. Okay, so this is something very, very important, and this reaction should be there in your notes also. Okay, so all the hydrides react with the water to evolve the hydrogen and thus behave as the strong reducing agents. As I already told you, whatever the hydrides are there, they react with the water with the evolution of the hydrogen. Since they are evolving the hydrogen, this hydrogen actually can add up to the certain reagent and reduce that particular substrate. Okay, so it is this magnesium hydroxide also reducing in nature. Okay, so here I have written beryllium hydride and the magnesium hydride. Beryllium does not react with the hydrogen, as I have already explained to you, and these two are covalent in nature. Please remember, these two are covalent in nature, and polymeric bridge structures are there for this one. And calcium hydride is technically known as the hydrolith, and all these are ionic in nature, while the first two are covalent in nature. And the stability of these hydrides decreases down the group as the size of the metal increases. Okay, now moving to the next slide. Before going into the next slide, I should have been given the structure of these, right, polymeric structures. So you can see how you can go for the polymeric structures, right? These polymeric structures are very, very important. So I may be given this structure in the upcoming slides, but right now you can understand it in that manner. You are having this beryllium. Okay, and again you are having this beryllium, and say you are having the polymeric chain of beryllium like that. Okay, so what you can do, you can place hydrogens over there in the middle of the two beryllium atom. You can put your hydrogens, okay, and then connect them to get the bridged structure. So this is hydrogen, this is hydrogen, this is hydrogen, and this is hydrogen. So it's a polymeric structure. And this polymeric structure is basically two-centered, is having the three-centered two-electron bond, 3C2E bond, right? And in case of the borane or the diborane, you have learned about this 3C2E bond, electron deficient compounds. So it forms a banana bond. If you go through the hybridization and the orbital picture, then you will be able to know what is the banana bond. If you don't know what is the banana bond, I'll discuss this in the upcoming lecture. So please remember, see, three center bonds are present in which your banana shaped molecular orbitals covers three atoms. Like what three atoms? Like you see your beryllium, hydrogen, beryllium. So this is actually the shape. This actually looks like the shape of the banana. So I can draw the shape of that banana just like that, right? This is your banana bond. Okay, and this contains only two electrons. So it's a three center two electron bond, where actually this hydrogen which is there, actually it is lie in the perpendicular plane to the plane of the molecule, right? If you see the 3D structure, and the stability of these hydrides decreases as we go down the group, which I have already explained to you. Okay, Now moving to the next very important property, solution in liquid ammonia. Okay, fine. So solution is liquid ammonia is another very important aspect, and this I have already told you in my last lecture, where I have explained you the color actually. So in that case, what is written here? Like alkali metals, the alkaline earth metal dissolved in the liquid ammonia to give the deep blue color. Okay, solution forming ammoniated ions. So these are the ammoniated ions and these are the ammoniated electrons. But the explanation is, see, in that case the explanation is not very proper here. So what you can do, you can learn that explanation to learn that explanation from my last lecture, where I have explained what happens with the concentration. See, initially when the solution is dilute, that means less ammonia is there, the solution is actually not that deep in color, but you keep on adding ammonia to it and the solution becomes concentrated in terms of the ammonia, then the color actually deepens, and this is true here also. You should know this point. Okay, so what basically happens, these alkali metals can also dissolve in the liquid ammonia to form the colored solutions, right? And dilute solutions are bright blue, as I already told you, which is not written there on the particular slide. Okay, and when you keep on concentrating the solution, that means by adding the ammonia, then this color deepens and it converts into the deep blue color. Only then, not initially. Only then, not initially. So slide is not actually the perfect in that case. Okay, and okay, from these solutions, the ammoniates, right, this one can be recovered, but concentrated solutions are bronze colored due to the formation of the metal clusters. Okay, so where the metal clusters are formed, actually this is something very important. Say what are the reactions? So what you can do, you can understand the reaction sequence also. Say for example, I am having the alkali earth metal, for example I am having the say calcium I am having. Okay, I am writing the reaction in that manner. You can use the instead of calcium, you can use the magnesium or the strontium also. So what will happen? It will form the calcium 2 positive ion and will liberate 2 moles of the electrons, or 2 equivalents of the moles of the electrons, not equivalent, sorry, 2 of ammonia, which is present as the solvent. It will grab these electrons, okay, and then hydrogen will be evolved from here, gas, and you will form the amide ion, 2 of NH2 negative, right? And after that, what can happen, the metal ion which you have formed in the first reaction, like calcium, they can react with these amides, okay, to form the metal amides. This is NH2 whole twice, right? This is the specific reaction about the calcium, but you can generalize it by taking M instead of the calcium, or you can replace this calcium with the magnesium or the strontium or the barium, whatever. Okay, so what actually happens, actually these reactions happens in the solution, and when the solution is evaporated, okay, when this solution is evaporated, so what I can do, I can write like that, evaporation. So what when evaporation occurs, actually, so this convert into the NH3 whole 6, right? This compound is formed actually, right? And this compound slowly decomposes into metal amides like M, NH2 whole twice, or since I have used calcium here, so what I can do, I can replace this with the calcium. Here ammonia will liberate from here, 4NH3, and hydrogen gas. The reaction goes like that, and concentrated solution of the metal actually are bronze in color, which is written here like that. So this is the ion actually, you should remember. Okay, so I have written in that case just like that. So where I made a mistake, 2 positive, sorry, I should have written like that. So this reaction sequence is already also important for you. Okay, now moving to the next slide, and of course before concluding this particular slide, you should know these are the good conductors of the electricity, because they are having the electrons, ammoniated electrons, okay, and the charge ions, right? And see, however, this property is much less pronounced in that in case of the alkaline earth metals, but it is more pronounced in case of the alkali metals. Halides, right. This we have to cover in pretty much detail, because these halides are rather important, and generally students have the question from this section in the examination, whether it is the academic examination or the competitive examinations. You'll always have the question from this particular section. And please remember one more thing. If see these actually group properties are very tedious and very fast, very vast. So there may be every chance that I have missed some questions, but whatever I will miss, I will definitely cover in the question answer sessions, right? So you continue to follow my lecture actually, right? Please continue to follow my lectures so that you can have the complete knowledge about the groups also. And these groups are very important. So in that case, you can see what is written here. Except for the beryllium halides, okay, all other halides of the alkaline earth metals are ionic nature. I have written here. Beryllium is more covalent in nature, and similarly magnesium is also having the significant covalent character, while your calcium, strontium and halides, they are more ionic in nature. So you know the Fazan's rule, polarization, the polarizability, and you know no bond is perfectly ionic, that is 100% ionic, and no bond is 100% covalent, and you have to apply the Fazan's rule where you can find the percentage ionic character in the covalent compound. So based on this Fazan's rule, you can say that beryllium and magnesium halides, they are more covalent in nature. That means they are having the more covalent character than the ionic character, and remaining calcium, strontium and the barium halides, they are ionic in nature. If you don't have any idea about the Fazan's rules, I am giving you the link in the description box, okay, and you can check the Fazan's rules. I missed the actually I forgot to put the link in my earlier alkali metal lectures, so I'll also put the links over there, which I have promised to give you in the description box in my last lecture. Okay, when it comes to the solubility in the water, then these MX2 are the water soluble, okay, and the solubility decreases as we go down the group, okay, and you know the your barium halides are less soluble, okay, and why this happens actually, because hydration energy also decreases when we move down the group, okay. But you know, when we are moving down the group, so ionic nature or the ionic character increases, and when the ionic character increases, it simply means that this will have the higher melting point, and conductivity also increases. So conductivity down the group increases, melting point down the group increases for these halides, okay. And they all are hygroscopic in nature. Hygroscopic means a degree of decrescent nature. That means the ability to absorb moisture from the atmosphere. And you know this calcium chloride which we use in the desiccator, it is a very famous dehydrating agent. So if you are in BSc actually, right, so you must be aware about the desiccator. Desiccator is a glassware which is used to drying the chemical compounds, and if you want to absorb moisture from the chemical compounds, then you use this calcium chloride as the dehydrating agent. It's a very famous one, okay. So your metal fluorides, right, so all your metal fluorides, so I have written Me here, it should be M actually, right, not E. Metal fluorides are exceptions, they are water insoluble, right, because these metal fluorides are much more covalent in nature, because fluoride is smaller one, right, and your metals are already there, so they are having the significant covalent character, so they are water insoluble. But among this, your beryllium fluoride is the exception, it is water soluble. Beryllium fluoride is the exception, which is water soluble. This is something very important. So you should remember the certain things actually, right? See this beryllium fluoride, as I already told you, this beryllium fluoride. So it is very water soluble. If you put this beryllium fluoride in the water, it is quite readily soluble. Why quite readily soluble? Because solvation energy is very high. So why this happens? So basically what happens actually when you take the beryllium fluoride, okay, BeF2. and if you try to dissolve this into the water, so what it results actually, it results BeH2O4 2 positive, okay, and it is having very high solvation energy of beryllium, okay. So this happens actually, then that means very high solvation energy is there in that case, and due to this, this is readily soluble in the water, while in case of metal fluorides like magnesium fluoride, calcium fluoride, this is not true, okay. So this is soluble while rest of the members are insoluble, like say if you are having magnesium fluoride, right, and if you are having calcium fluoride, okay, if you are having strontium fluoride, if you are having barium fluoride, F2 BaF2, they are insoluble in water, and this is readily soluble due to the formation of this particular ion. This is something very, very important, okay. And now you can see here fluorides of the other metals, like these, they all are ionic in nature. Please remember, they are ionic in nature, they are having the very high melting points, okay, but they are water insoluble. So it is a little bit of in the contradictory side. Generally ionic compounds are soluble in the water, right, but these metal fluorides, though they are ionic in nature, but they are insoluble in water due to the very low solvation energy. So when solvation energy is very, very low, that means your compound will not dissolve into the water, and in that case your solvation energy is very, very high. In case of the beryllium fluoride, that's why it is water soluble, so high solvation energy. In that case you can see here beryllium chloride is there. So if I go back, right, you can see these are the beryllium hydrides, these bridge structures, okay, and here also you are having the bridge structure of the beryllium chloride. Both actually are looking same, but they are not same actually, they are different. So this is this need to be understood. So when you are beryllium chloride in the solid state, please remember, when beryllium chloride in the solid state, it forms a polymeric structure, which I have shown you here, just like your beryllium hydrides, okay. And after that you can see if beryllium chloride in the vapor state, right, then in the vapor state it can form the dimer or it can form the monomer. So I have shown you the monomer here, and similarly you can also form the dimer here. But this compound is little different from the other types of the compounds. Let's check whether I have written in the, so you can see here what is my first question. Why beryllium fluoride is water soluble? Okay, this I have discussed, guys, okay. Due to the very high solvation energy, beryllium fluoride, though having the covalent character, but it is water soluble, okay. So actually I forgot that I put this question here, because I prepared these slides way long back actually. I forgot what I have put it in that slide and what not. That's why this problem is there. So it is soluble, see, though covalent, so I am writing though covalent, highly covalent, okay. It will have the certain degrees of the ionic character also, but due to high solvation energy, it is water soluble. So the next question is how BeCl2n differs from the BeH2n. See, both actually will have the three-centered bond. Please remember, both having the three-centered bond, and they are looking quite similar, but they are different, right? So if you remember, in case of I was having three-centered 2-electron bond. Why? Because hydrogen is not having any electron. It is electron deficient. It is not having electron. But in case of the halogen, you are having what? Lone pairs. So when you are having the lone pairs, that means the lone pairs can be easily donated to the beryllium. So if I draw the dimeric structure, like see beryllium here, and your another beryllium is here, and you are having the, say, one chlorine here and your another chlorine here. So what it can do? This chlorine can donate electron to this one, okay, and this chlorine can donate electron to this one. So actually the bond pair is coming from the halogen itself, and this is the normal bond, this is the normal bond, right, and then you have Cl and Cl. So in that case actually no banana bond, while in case of the hydride you are having the banana bond. So this needs to be understand. So basically what happens actually, when this bridge is forms, in which a halogen atom bonded to the one of the beryllium atom uses a lone pair of the electron to form the coordinate bond, while this is not possible in case of the hydrogen, right? I hope this is clear now. Now next is what? Anhydrous beryllium chloride cannot be prepared in aqueous solution. Why? Okay, that means, see, if you want to prepare, say, magnesium chloride, okay, or if you want to prepare calcium chloride, so you can easily form in the aqueous chemistry, right? In the aqueous solution, you can easily form them in the aqueous solution, right? And if you want to synthesize them, or if you want to form them, if you form a beryllium chloride in the water, then it is not possible. And why it is not possible? I already told you. It actually takes up water and to form a complex ion. Okay, that's why it is not possible. So well, in aqueous solution, what actually happens? Your beryllium forms these ions. This I have already told you a few moments back actually. So you know, it is tetrahydrated beryllium complex. Okay. So actually this compound results instead of your barium chloride, if you take the halogen acids along with the water, right? So this compound formed instead of your beryllium halide. And if you want to say, suppose it is present in the form of this halide, right? Say for example, this present like that, Cl2 is there. So when I am putting the Cl2 here, so what I can do, I can remove 2 of the charge from here, and say from this compound, if I want to decompose it, right? Say for example, if I heat this particular complex of the beryllium, so it will result in the beryllium hydroxide, okay, and 2 of the HCl will remove from here, 2 of HCl along with the water. So you are not getting your beryllium chloride. Okay, so it is not possible in the aqueous solution, while this is possible in case of the other alkali metals, but in case of the beryllium chloride or barium halide, it is not possible. So basically your anhydrous halides, they are best prepared by the some other different reaction. You can take the, say if you want to synthesize it, so let me give you the thing. So if you want to synthesize this beryllium chloride, so you can better take your beryllium oxide and you combine this beryllium oxide with the carbon in the atmosphere of the chlorine. Okay, of course your high temperature is required in that case, around 700 degrees centigrade. Okay, only then it will convert into the beryllium chloride and your carbon monoxide, right? This happens like that. Or sometimes you can take your organic solvents also. So for example, you are having the beryllium oxide and you are taking your carbon tetrachloride. Okay, so in that case also, however, the higher temperature, again somewhere around 800 degrees centigrade is required. So it will form the 2 of the beryllium chloride, 2BeCl2. Okay, and carbon dioxide would remove from here. Since 2 to the 4, 4, 2. So 2 of beryllium oxide is required here. And structures actually I have already explained to you. Your beryllium chloride in the vapor stage, it will exist as a monomer or the dimer, that is BeCl2 or BeCl2 whole twice, while in the solid state it is polymerized. But the structure of the polymerized form of the beryllium hydride and the beryllium halide is different, as I have already explained to you. Okay, now moving to the next slide. Industrial applications of calcium fluoride. Calcium fluoride is white. You should know the color of this particular compound, right? It is a white solid, and insoluble high melting solid. White high melting point solid, and it is water insoluble. Okay, please remember it is water insoluble also. And it is very important. So why it is important? Say you are having the calcium fluoride, CaF2, and if you dissolve this calcium fluoride in the acid, because it is not soluble in the water alone, so it will give you the hydrogen fluoride, HF, and you know the HF is used in the scratching of the glass, CaSO4 it will result, and you know this is used in the scratching of glass. So this is important application of HF, which is coming from the calcium fluoride. Okay, and this hydrogen fluoride which is formed here, if it is combined with the potassium fluoride, so it will form your potassium hydrogen fluoride. And if you do the electrolysis of this one, so you'll get the fluorine. Okay, and you know the fluorine is having large number of the industrial applications. So basically this calcium chloride, one more application of this calcium fluoride is what, in the spectrophotometers, cell windows for spectrophotometer. Okay, and it is also used in the making of the prism. Okay guys, so next important compounds of alkaline earth metals are the salts of the oxo acids. That mean the salts which contains the oxygen atoms, they are known as the salts of the oxo acids, and the main examples of these oxo acids are the carbonates. And these carbonates are very important when it comes to the water hardness. See, in a little while I will also discuss the hardness of the water. Okay, so what you can see here, alkaline earth metals, they also form the salts of the oxo acids, and carbonates of the alkaline earth metals are insoluble in water. So whatever you are having, say if you are having your calcium carbonate, okay, and it is water insoluble. In fact, in case of the water treatment, when you do the water chemistry and you are looking for the water hardness, this calcium carbonate is the most insoluble substances in that case. Okay, and it will not cause any kind of the hardness. Later I will discuss why. Okay, and similarly you may have your magnesium carbonate. Okay, and like that you may have your strontium carbonate. So various carbonates are there, and these all carbonates are insoluble in water. If you try to dissolve these carbonates in the water, then they remain insoluble one. However, if you pass the carbon dioxide through the saturated solutions of these carbonates, they can be made dissolve. Okay, why? Because they form the bicarbonates. In that case, you can focus on this particular reaction. Say my calcium carbonate is there, which is the most insoluble substance during the water hardness. Okay, and if you try to dissolve this into the water, it will remain undissolved or insoluble. But to this particular saturated solution, if you pass the carbon dioxide gas, then this carbon dioxide dissolve. Why? Because this calcium carbonate dissolves, because calcium bicarbonate is the product in that case. Similarly, you can do this reaction with your magnesium carbonate as well as your strontium carbonate. Okay, so this is how you can prepare. What you can do, you can take these carbonates, right, and you can prepare them, you can dissolve them by using this particular method. So this is something very important. Okay, so in this way carbonate dissolve in the water, which contains actually the carbon dioxide. And you should know a very important thing. So basically, if you have these carbonates, right, say you are having the say you are having magnesium carbonate. Okay, this is something very, very important. Okay, and you may have your, say, calcium bicarbonate, which you have just seen here in that case. Similarly, you may have the magnesium bicarbonate. Okay, so these bicarbonates generally present in the water sample, and they causes hardness in the water, and the hardness which is due to the soluble carbonates and the bicarbonates of your metals, especially calcium and magnesium, they cause the temporary hardness. Please remember. Okay, so I have made an extensive lecture series on the water chemistry and the water hardness. So I'll not discuss the details of the water hardness in that case. And if you want to know how the water chemistry goes, then you can type water treatment by tetrahedron chemistry classes in the YouTube search bar. You will get the results. Okay, so I have discussed all these things there, which you should remember. Okay, now the next very important thing is what you see what I have written here. The solubility of the carbonates in water decreases as the atomic number of the metal increases. So what is the meaning of that? Say, let me quickly remove all the things. Okay, say you are having, so you can see here you are having your beryllium carbonate, and after your beryllium carbonate you are having your magnesium carbonate, and after magnesium carbonate you are having your calcium carbonate, and then you are having your strontium carbonate, and then lastly you are having your barium carbonate. So these are the carbonates, and as you go down the group the solubility decreases, right? So if you go down the group, then the solubility decreases. So why the solubility decreases? See, as the atomic number increases, earlier in this particular lecture I have already explained to you, when the hydration energy decreases, the solubility also decreases. Okay, so you should remember this particular point. So the insolubility, why this actually why this solubility decreases as we go down the group? Because decrease in the hydration enthalpy. And then after that you can see all the carbonate decompose on heating to give the carbon dioxide. Again this you should remember, whatever the carbonates are there. I can take the example of the calcium carbonate. Okay, if I heat this calcium carbonate, please remember it is something very important. If I heat this calcium carbonate, so it will decompose to calcium oxide with the liberation of the carbon dioxide gas. So this is a very important reaction. Why? Because this calcium oxide is also known as the lime. So if you want to prepare, or if you want to produce lime, then you can produce lime by the decomposition of the calcium carbonate. In the similar way you can decompose this magnesium carbonate, right, to produce your magnesium oxide, right, and so on. And the important thing is that, see, along with this your oxo acids like your carbonates, these alkaline earth metals also form the nitrates. Okay, and here what you can see, what I have written here, all the carbonate decomposes on heating according to this particular reaction. And here you see the important thing is that I have explained for the calcium, and I also told you that you can do the same thing for the magnesium carbonate and the strontium carbonate and barium carbonate as well. But beryllium carbonate is unstable and can be kept only in the atmosphere of the carbon dioxide. That means this kind of the decomposition actually would not be possible. Why? Because this beryllium carbonate is having tendency to absorb the moisture from the atmosphere. Okay, so it is actually quite unusual. So it gets hydrated. If you keep this in the absence of the carbon dioxide, it will take the moisture from the atmosphere. Okay, and it will get converted into this tetrahydrated ion. Okay, so I can put Be2 positive. This actually product or this complex ion you have seen already many times earlier in my lecture. Okay, so you will not find this Be2 positive, and you will find this particular complex ion. This is something very important. Okay, and then the next thing is that when we move down the group, the stability of these carbonates actually increases. So what I can do, I can again remove certain things. So why actually the thermal stability increases when we go down the group? Because when we go down the group, ionic nature increases, ionic character also increases. So as you can see, when we move down the group, the carbonates of your alkaline earth metals, their thermal stability increases as well as their ionic character increases. So why actually this happens? You know, your beryllium, Be2 positive, it's a very small ion, right? And this on this small region, 2 positive charge is there. Okay, so high charge is concentrated in the very small region, so its polarizing power is very high polarizing power. So what can happen in that case? Say for example you are having your carbonate ion, and when this beryllium 2 positive ion comes closer to the carbonate ion, so the electrons present on the carbonate ion will be highly polarized by the very small beryllium ion. And you know, when this polarization occurs, then covalent character increases. So basically this beryllium carbonate is having high covalent character. So what I can do, I can write here character, right? And now as you move down the group, the size of the metal ion increases. That means magnesium is little bigger than your beryllium, and calcium in turn is much more bigger than your beryllium, and strontium actually is again very much bigger in size when compared to the calcium, magnesium or the beryllium. So when we move down the group, the size of the metal increases, right? So due to this increased size, polarization power decreases. So your magnesium, calcium, beryllium, as we go down the group, say for example if I take the barium, So this barium is having very low polarization power. Okay, that means it cannot polarize the cloud of electron cloud of the carbonate ion pretty much. So it will have very less covalent character. That means it will have high ionic character. High ionic character. It is having very high ionic character, and you know your ionic compounds are more thermally stable than the covalent compound. That's why when we move down the group, thermal stability increases. And this is not only true for the carbonates of the alkaline earth metals, it is also true for the nitrates of your alkaline earth metals, because they also form the nitrate. These, however, you can think in that manner that when we move down the group, ionic character increases. That means the solubility also should increase in the water, but solubility is not actually increasing down the when we move down the group for these carbonates. Solubility decreases. Why? Because hydration enthalpy or the hydration energy also decreases when we move down the group. Say your beryllium carbonate, right? It is actually decomposes somewhere around 100 degrees centigrade or less than 100 degrees centigrade. When you move for the magnesium carbonate, so it is thermally stable up to 540 degrees centigrade. Your calcium carbonate is rather more stable, up to 900 degrees centigrade. Okay, and your strontium carbonate is stable somewhere around 1290 degrees centigrade. And you know barium carbonate is exceptional. It is thermally stable up to 1360 degrees centigrade. So next is the sulfates, right? Sulfates again the very important class of the compound, and in fact you can find many applications of these sulfates, right? And again, see, water chemistry is there. Say earlier what I told you, bicarbonates and the carbonates of the alkaline earth metals which are soluble in the water, they can cause your temporary hardness. But if you have the calcium sulfate, right? Say for example, if you are having the calcium sulfate or you are having the magnesium sulfate, okay, so these are responsible for the permanent hard. That means water is said to be permanently hard if it contains your calcium sulfate or magnesium sulfate along with the chlorides also. Okay, or why it is then called the permanently hard? Because you have already seen that in case of the calcium carbonate, when you heat it, it produces lime, that is CaO, right, along with the carbon dioxide. But this reaction, right, if you have your calcium sulfate, for example, if you heat it, okay, so it will never give you your calcium oxide plus SO3. Okay, so this reaction actually is not possible. That's why this water is said to be permanently hard when the sulfates are there. This is something very, very important. And now the next thing, say for example, the sulfates of the alkaline earth metals are all white solids. See, you can check the calcium sulfate is white, okay, and your magnesium sulfate is also white, and they are also stable to the heat. That means they are thermally stable. Say for example, you are having your beryllium sulfate, okay, and the important thing about them is that the first two, they are water soluble, but as you move down the group, the solubility actually decreases. Solubility decreases. And why the solubility decreases, guys? Again, due to the lower hydration enthalpy. In fact, your barium sulfate is practically insoluble, right? It is not soluble in the water sample. However, your calcium sulfate is sparingly soluble. Okay, but you cannot dissolve your strontium sulfate, right, and your barium sulfate or your radium sulfate. They actually remain insoluble in the water. Okay, so you can see here I have also written in this particular slide, okay, the greater hydration enthalpies of these two, right, because they are having the little bit smaller size, so hydration enthalpy is quite high in that case, right, which overcomes the lattice enthalpy. That's why these two are soluble, while for all these hydration enthalpy is quite low actually, right. That's why they remains practically insoluble in that case, right. And various other compounds are also there which are very, very important industrially. Say you are having your magnesium sulfate, MgSO4 and 7H2O. So you have studied your chemistry in everyday life in your class 12. Okay, so what is this? This compound is what? This is known as Epsom salt, and this Epsom salt, because it contains the magnesium, and after the consumption it can form the magnesium hydroxide. So it's a mild laxative, which relieves the constipation. As I already told you, magnesium hydroxide is readily used in the antacids. Okay, and then you are having your next sulfate, say calcium sulfate, CaSO4. It also gets hydrated, but only half of the water molecule is there. And I hope you know what is this compound actually. Okay, what is this compound? If you remember, this is what? Plaster of Paris. Basically, this calcium is forming hemihydrate. Hemihydrate means CaSO4 dot of half H2O. Okay, and this actually as see, the brand name of this particular hemihydrate is the plaster of Paris. And this plaster of Paris actually produced by the decomposition of your dihydrate. So if you want to synthesize this, say you are having calcium sulfate, okay, dihydrated 2H2, and if you heat it at 150 degrees centigrade, I hope you know this calcium sulfate dot 2H2O is what? It is a very important compound used in the cement industry, that is gypsum. When you heat it, then it will give you the plaster of Paris. If you further heat it, say somewhere around 200 degrees centigrade, so it will form the anhydrous salt, CaSO4. Without water, that means anhydrous. And at very high temperature, please remember, at very high temperature, somewhere around 1100 degrees centigrade, it may decompose to give you. However, in my last slide, I told you that the decomposition of calcium sulfate is not possible to give you calcium oxide and the sulfur trioxide, right? Of course, in water chemistry it is not possible because that much of high temperature is not available in the water chemistry. But if you heat it at very high temperature of your 1100 degrees centigrade, then you can of course decompose it. Okay, please remember, it is something very, very important. And this plaster of Paris is having enormous amount of your applications, like your say if you want to plaster your walls, then you will use this one. Okay, and sometimes in the medical also, right, in the medical field also, when the person is suffering from the fracture, then that fracture actually needs to be fixed actually, and the fixing of this fracture is actually done by the plastering, and in that case your plaster of Paris is used. So these things are very, very important, which you should know. Okay, and again the same thing when you move down the group. When you if I go back, when you move down the group, thermal stability for them also increases. Okay, please remember, as I have explained for the carbonates, in that case also thermal stability increases. So I can write stability or thermal stability, both are same thing, increases. The reason is quite same. Okay, reason is quite same, because beryllium sulfate actually you decomposes somewhere around at 500 degrees centigrade. Okay, and this magnesium sulfate somewhere around 895 degrees centigrade. Okay, if you keep on moving, then you will have the other values also, but data is not very important. You don't need to bug out all these data, right? It would be given in the examination if needed. Okay, next are the nitrates. So nitrates also behave similarly, like all the things are same for the nitrates, as I have explained for the carbonates as well as for the sulfates. Okay, but there are certain important applications. Okay, please, you should remember. Here you can see the nitrates are made by dissolution of the carbonates in the dilute nitric acid. It's simply, if you want to prepare these nitrates, what you can take, you can dissolve these carbonate in the dilute nitric acid, then you will get your nitrates. Magnesium nitrate crystallizes with 6 water molecule. It should be noted. Okay, magnesium nitrate, MgNO3. It crystallizes with 6 water molecule. And your barium nitrate, actually it is anhydrous. Okay, so it is not having any water molecule. And these nitrates, again you can see those they show a decreasing tendency to form hydrates when we move down the group, like I have explained for the carbonates. Okay, right, because hydration enthalpy decreases. However, all these nitrates, whether your magnesium nitrate, your beryllium nitrate, okay, your calcium nitrate, whatever, right, they can produce your oxide, like I have explained for the lithium nitrate. Okay, lithium nitrate also decomposed, right? While all other nitrates do not decompose of your alkali metals, but in case of your alkaline earth metals, all the nitrates can be decomposed, right? So not barium nitrate. I am taking the example of the magnesium nitrate. Okay, say I am having my magnesium nitrate. Okay, so what I can do, I can heat this magnesium nitrate, and when I heat this, I'll produce monoxide of this one with the liberation of 4 of NO2. Okay, and you will also have the oxygen in that case. So if you want to balance this particular reaction, then what you can do, then you will take 2 of this. Okay, so this is how you can decompose them. So your alkaline earth metal, generally they form the nitrates of this kind. Okay, this kind. And but they are water soluble. Please remember, nitrates of these metals are water soluble. The solubility is there, they are water soluble. They all are water soluble. So you can see here very important feature which you should remember. Beryllium also forms this nitrate. Okay, the normal nitrate which is there. But if you actually heat this beryllium nitrate, okay, somewhere around at 125 degrees centigrade, so it forms the basic nitrate also, which is covalent in nature. Basic beryllium nitrate. Okay, so this property is only for your beryllium nitrate, while other metal ions cannot form these basic nitrates. Okay, they also form the carbides. Alkaline earth metals also form the carbides, right? Ca, C2. And then these carbides are important in the synthesis of the organic compounds. If you remember that certain hydrocarbons actually are produced by using the reaction of your sodium on the carbides. See, in class 9th and 10th, I think you have studied these reactions. Okay, so if you want to produce these carbides, how we can produce these carbides actually? Say for example, I am having my beryllium oxide. Okay, and what I can do, I can take carbon, and along with the carbon I can heat this at very high temperature, somewhere around 2000 degrees centigrade. Okay, then it result into which is the beryllium carbide. Okay, and it is red in color. Please remember, it is red, brick red in color. This is ionic in nature. So the very important application of this beryllium carbide is what? Okay, so what you can do, if you are having this beryllium carbide B2C, you can dissolve this into the water. Okay, and when you dissolve this into the water, it will form hydroxide of this beryllium. Okay, along with the liberation of the marsh gas or the methane gas. Okay, and to balance it, you can put 2 here, because it is forming this carbide is forming methane, so it is technically known as the methanide. So apart from this beryllium carbide, you may also actually think about your calcium carbide, which is again very important in the various applications, right? Say for example, you are having this calcium carbide. Okay, your calcium carbide is CaC2. So why this actually this compound is important? Okay, so the important thing is that when you react this compound with the nitrogen, okay, and see, of course the temperature would be very high in that case. This reaction will not happen because atmospheric nitrogen is quite unreactive. Okay, and if you want to react this nitrogen with this with the particular compound, then you have to heat the reaction mixture to a very high temperature. So if you heat this calcium carbide along with the nitrogen, right, at a very high temperature, it will form a very important compound which is known as the CaNCN. Okay, this is very important compound, and of course your carbon would be removed from here, black carbon. Okay, or carbon black you can call it as. And this ion basically, right, say if you try to make this Ca2 positive, and then this ion would be there. Since your calcium is 2 positive, you can put 2 negative over there. So this ion actually which results which results by the ionization of this particular compound, this is known as your cyanamide ion. This cyanamide, guys, is very important. As you can see here, it is actually consuming nitrogen. Okay, so this actually cyanamide is regularly used to actually synthesize the nitrogenous fertilizers, and this is having added advantage over the other nitrogen fertilizers, because this cyanamide actually hydrolyzes very slowly over a period of the month. Okay, so this calcium cyanamide is having extra advantages, because other nitrates, say if you are having other fertilizers, you can think of this ammonium nitrate. Okay, if your ammonium nitrate is there, so along with the ammonium nitrate you can have your urea also. Urea is more famous than the ammonium nitrate. Okay, urea. So they are also nitrogenous fertilizer, and this calcium cyanamide is also your nitrogen based fertilizer. Importance of this calcium cyanamide is that, see, it will not wash away with the rain. So generally what happens, if you put these nitrogen based fertilizers like your urea and your ammonium nitrate in your crop field, right, and suddenly, say, in the monsoon season, suddenly in the monsoon season, if rain occurs, then all these nitrates and the urea actually washed away with the rainwater. But this calcium cyanamide, this actually remains intact in the field. So this is having added advantage for the farmer. Okay, that's why it is important one. And there are many other industrial applications also for these calcium cyanamide. Like you can manufacture your hydrogen cyanamide. Okay, and after that, with the help of this hydrogen cyanamide, you can produce different kinds of the compound. Okay, and see, there are various reactions. However, it is not possible to cover all these things in this only one lecture. And say for example, you are having your calcium cyanamide. Now Ca and Cn, right, you are having this one. What you can do, you can dissolve this into sulfuric acid, and when you dissolve this into sulfuric acid, okay, you form this particular compound, right? And then along with this, you will also have the calcium sulfate. This you can very easily form. Okay, and this compound actually is very important. If you fix the pH of the solution, right, if you fix the pH somewhere around 9, at 9 pH, okay, so basically it will form diacyanamide. This is diacyanamide, and this diacyanamide, if you do the pyrolysis or the cracking of this one in the absence of the oxygen, pyrolysis is what? Heating in the absence of the oxygen. So it is produce a heterocyclic compound. I can write the structure of that heterocyclic compound here. So basically this is your melamine, and basically it is this is cyanuric acid. Okay, now next thing is the anomalous behavior of your beryllium. Like lithium, your beryllium is the first member of its group, right? So it is also having the anomalous behavior, and there are various kinds of the things actually which actually beryllium does, and rest of the members actually will not show those properties. So why this anomalous behavior is there? As I have explained for your alkali earth metals also, it is having very high electronegativity because it is very smallest one. See, however, see, in the group actually it is having higher electronegativity, right? However, it is not that electronegative when it comes to the halogens or the nitrogen, etc. Okay, but in its group actually it is small in size, so it is having the high electronegativity. And of course, its atomic radii as well as ionic radii is again very small. So due to this actually it shows the various different properties, right? It is also having the very high ionization energy. So due to the high ionization energy, smaller size, high electronegativity, it actually behaves distinctly from the rest of the members of the group. Okay, so what are those actually? You can see here, beryllium is hard metal, while other alkaline earth metals are soft actually. Okay, so beryllium, in that case, it is least metallic in nature, and it forms the covalent compound. You have already seen few examples of this, okay, like I have explained for the beryllium carbonate, beryllium nitrate, okay, and this is easily hydrolyzed. You know, it forms the tetrahydrated ion. So it is important to keep the beryllium carbonate in the atmosphere of the carbon dioxide, otherwise it is formed your hydrated ion, not simple Be2 positive, but it will form the BeH2O4 2 positive, okay. Its melting point, boiling point, ionization enthalpy is highest among all the other among the group actually, while rest of the metals actually are having a low melting, boiling and ionization enthalpy in comparison to the beryllium, okay. And in case of the oxides and the hydroxide, I know I actually already told you this actually your amphoteric in nature, okay, while other hydroxides and oxides, they are basic in nature. Beryllium will not liberate any kind of the hydrogen when you put the beryllium into the HCl or H2SO4, but other alkaline earth metals, when you put in the acid, actually they produce hydrogen. So I forgot to put this particular reaction, but I can give you the example. Say for example, you are having calcium and you put this calcium into the HCl. So what will happen? You will have the calcium chloride along with the hydrogen. So it can liberate hydrogen, okay. So if you want to balance this reaction, you can take 2 moles of this. However, this reaction is not possible when you do the same reaction with the beryllium, okay. And your beryllium does not show coordination a number more than 4, right? Okay, more than 4 actually, right? Coordination number is more than 4. Just say for example, you have already seen this 2 positive, okay. So this coordination number is only 4 in that case, okay. So this 4 actually is not here. So if I want to correct it, so what I can do, I can remove this from here and I can put my 4 here, okay. And why this happens? Because d orbitals are absent in that case, so it cannot accommodate other ligands around itself, okay. So that's why it is show only the 4 coordination number. Like your say beryllium has very strong tendency to form the complex compounds, as you can see here in that case, while others are not very keen to form the complexes, okay. And in the flame color, right, I already explained to you that beryllium is not actually beryllium does not show any important color in the flame. And beryllium sulfate is if you have the beryllium sulfate, right, BeSO4, it is water soluble, while the solubility decreases when we move down the group. So all these things actually I have explained. There should be something which must be there in the lecture, that is the diagonal relationship, okay. You know, it happens this diagonal relationship actually happens in case of the second and the third period of the compound, okay. So what you can do, say you are having beryllium, okay, and you are having your magnesium, you can write in that manner, and you are having boron. After that you are having boron, and this is you are having aluminium. Basically it is group 2, no, and it is your group 3, okay. And you know, this is your second period and this is your third period, and this beryllium is diagonally placed with respect to the aluminium in the periodic table. So they actually are having similar properties, but there should be a certain reason behind this. So see, I am not writing everything on the slide. What you can do, you can listen carefully and make your own notes by pausing the video if you want. Otherwise textbooks are there to explain all these things, okay. So both, whether you are beryllium ion or you are aluminium ion, right, say you are having beryllium ion Be2 positive and you are having your aluminium ion Al3 positive, right. So if you compare these two ions, right, so they both are having very high polarization power, and again their electronegativity are also same, not exact value but approximately same, and their reduction potential is also same. So all these things actually makes them similar towards the various kinds of the reagents, and they show the various kinds of the similar properties. Okay, you know your aluminium oxide, your aluminium is prone to oxidation, further oxidation. Why? Because it's from the Al2O3. And if you know the Pilling-Bedworth rule, Pilling-Bedworth rule we generally study in the corrosion chemistry, right? So what the Pilling-Bedworth rule says, that when the oxidation of the particular metal occur and the oxide is formed, like I have formed this aluminium oxide, right? So it's a protective coating. It actually covers the surface of the aluminium, fresh aluminium completely, and the penetration of the fresh oxygen will not occur, because the surface area is very high for this one. So it is corrosion resistance. In the same way, your beryllium also resistant to the oxidation, or say the corrosion. So they are actually, they both are unaffected, like the beryllium as well as your aluminium, both are unaffected by the atmosphere. The decomposition of the beryllium actually would not occur in the water, and this is also true for the aluminium. And if you want to know some other reaction, right, say for example you are having beryllium metal and you try to dissolve this beryllium into the sodium hydroxide, so it will form a compound, a kind of a salt with sodium, with the liberation of the hydrogen. That means from the alkaline solution, right, beryllium can liberate hydrogen. And same reaction, say if you are having your aluminium, okay, and you are reacting this aluminium with the sodium hydroxide, of course your water is needed here in that case. Okay, so it will also form the same kind of the salt, 2Na-AlO2, sodium meta aluminate with the liberation of the hydrogen. So aluminium can also liberate hydrogen. So if you want to balance the reaction, you can various other reactions are also there. Say for example, if you are having beryllium oxide, right, and if you dissolve this beryllium hydroxide into sulfuric acid, so it will form the beryllium sulfate, BeSO4, along with the water. So this must be true for the aluminium also. Okay, now say suppose I am having my aluminium oxide, which is alumina, Al2O3, and I put this alumina into the HCl. Okay, so it will form AlCl3, aluminum chloride, and of course water molecules would be there. If you want to balance this reaction, you can do easily, right? 2 of this is required, that means 6 of HCl would be there. Okay, then 6, that means 3 of H2O would be there. So in this way you can balance the reaction also. Say for example you are having your beryllium hydroxide, BeOH whole twice. If you react this with the HCl, okay, it will form your halide, BeCl2, in the water, and it is insoluble. Please remember, this is insoluble. Likewise, you can take your aluminium hydroxide and you can put this aluminium hydroxide into HCl. Of course 3 of HCl would require in that case. However, if you heat them, these hydroxide, if you heat them, then you can decompose them. Okay, and see, aluminium also form the polymeric compound, beryllium also form the polymeric compound. Basically polymeric hydrides they form actually. And say if you are having your beryllium, it can combine with the nitrogen and it will form the beryllium nitride. The same reaction is also shown by the aluminium also. So you can write 2 of Aln, aluminium nitride. So in this way they show the diagonal relationship. Group 2 elements are also important, and among those, calcium is very important. Basically 23 essential elements are required for the human body, and out of these 15 comes from the S block elements. You know, sodium from the S block elements, potassium from the S block elements. Now the calcium, you know, half of the world, please remember this thing, half of the population of the world is suffering from the deficiency of the calcium, right? And this is the reason for the weak bones, right? And see, if you want to know the biochemistry or the bioinorganic chemistry, if you want to learn, then, or if you try to learn, then you will understand that when you have the deficiency of the calcium in your body, then definitely you will also have the deficiency of the iron, because the absorption of the iron takes place in the presence of the calcium. So if the body is calcium deficient, then you will also anemic. That means iron deficiency would also be there. This is the reason in the Ayurveda they mention the betel, pan. This pan we already know. Lots of people are very fond of this pan, and this is mentioned in the pan is basically betel, right? Betel leaf. Okay, and this is mentioned in the Ayurveda also. If you put some of the lime over there, right? Chuna, which you used along with your surti or some tobacco, right? This is very very important, lime, and this needs to be there in your diet also. See what we people do actually, we take the very very expensive and costly supplements to actually overcome the problem of the calcium. However, I think there is no need to go for those expensive supplements. You take a little of lime actually, right? And you put on this here on the betel leaf and consume it regularly. And you can put a pinch of this tuna into your dal, or you can make a mixture of a little, say a pinch of this calcium carbonate into the water, and try to dissolve it. Whatever the amount will dissolve, filter it and drink the water. So it will actually it will be more helpful or more beneficial than the expensive your calcium supplements. And after that, your magnesium is very very important. Okay, and this magnesium is very important component of your chlorophyll, right? If magnesium is not there in the chlorophyll, then you will not have the process of the photosynthesis, right? So there are various important things which you need to understand about these elements. However, it is not possible for me to include all the things in the literature in the one or two lectures. You actually, if you are interested in learning all these things, then you can learn by your own also. Basically, you see, 90 gram sodium is there in the human body, 5 gram potassium is there, okay, magnesium 25 gram, calcium is 1200 gram, okay, 1200 to 1400, it varies according to the age. Okay, all these things are there. So I hope I have covered all the important things about your alkali metals are in this particular lecture, alkaline earth metals. Okay, and in the next lecture I will meet you with the question answers, right? So how we can approach to solve the questions based on these things. Okay, so that's it for today. And if you are new here watching video for the first time, please subscribe the tetrahedron chemistry classes and do share with your friends also. So that's it for today. So thank you very much. Thanks for watching.